there. This is the Thanksgiving lecture for CPE129, Cal Poly, Fall 2010. Today we are going to talk about a little bit more about VHDL and implementing sequential circuits in VHDL. We talked about some of the structures used in VHDL to make sequential circuits possible. And the main one was the process statement. And if you remember the process statement, as process, you can have the process name over here followed by a colon. But this process, that's a keyword and you need to use that. Okay. Then there's usually a list after process. Right here, there's in the list after process is CLK or clock. That is the sensitivity list. Whenever a signal in that list changes, this process will be called and the code inside that process will be run. That code will not be run unless the signals in the sensitivity list are change. Okay, so that's the first thing, just reviewing. And another thing that I hope you remember is that inside a process there are a lot more things you can do. It looks a lot like one of the programming languages you've seen probably before this class. You can use if statements, for statements, case statements, and you couldn't use that directly inside an architecture before, inside the data flow architecture. I'm not sure where the list is. Yeah, all these things here that you couldn't use in the case statement. Okay, today, I think in the program I'm going to be talking about today, the main structure that we will use, the main data flow format that we'll use is the if statement. If, and then a true or false statement, and then if this is true, this line's run. If it's not true, then it goes to the else statement. If there's no else statement, then it just doesn't do anything. So this is the main structure that we're going to use today. Inside a process, between the process keyword and begin, you can declare a variable. A variable is like a flip-flop. It holds a value in between calls to this process. It also has the characteristic that as soon as it's set here, its value changes. Unlike a signal, which we mentioned, doesn't change until the next clock cycle. Here's a for statement. I don't think I used a for statement here. Remember I did in the original code, but changed it. But if you notice, there's this I right here. If you remember, that's a temporary variable, and when you use this for statement, VHDL creates the memory for that variable without you having to declare it up inside your at the beginning of your process. Okay, we also had a couple of handy functions here. Rising edge tells you if the clock, which remember that was in the sensitivity list, so every time the clock changes, your process is called. But if you want to build something that is a rising edge triggered, some rising edge triggered code, then you need to see if that clock has changed from 0 to 1 or 1 to 0. 1 to 0 is a falling edge, and if it's a rising, if you want your process run on a rising edge, then you need to check and make sure that whether the change in the clock was a rising edge or a falling edge, and then only do your run your code when it's a rising edge. Okay. Oops. Okay. Actually, the last thing that I'm going to show you in these slides before I go on to the example code that I have in that other document that's posted on Blackboard is the method used here, which is to declare my own type, my own data type. So there's integers, there's booleans, there's standard logic vector. You can also declare your own data type. And this data type, this statement right here, says type, and then you give it whatever name you want to give it. I named mine state type because these are going to be state values. Remember when we draw our state transition diagrams, there's that first name that's user friendly. I want to use those names instead of the ones and zeros that the name given in ones and zeros that we've been using so far. So give it type, and then give it the name that I want to give it, and then is, and then there's a list of values right there. You can consider those as names or as text, and they are the only values that, right here, a signal. I've declared this signal. I've declared signal CS and NS as a state type, and that means that the CS and NS can only have the values S1, S2, S3, S4, S5, S6, or S7. Okay, if you try to put another value into CS or NS, I believe you'll get an error, it will tell you that that particular type cannot have the value that you're trying to put into that particular signal. Let's see, I think that's all the slides here I wanted to go through. Okay, so what we've seen there, we've seen the process, which has a sensitivity list. The process will only be called when something in its sensitivity list changes. We've seen rising edge and falling edge, which are functions that look at a signal or when something in your sensitivity list has changed, it can see whether that value has changed from a low to a high or a high to a low. Okay. Then we saw a new thing where we can declare our own types, and we can tell VHDL that we're going to declare a type that only has particular values. And in the example I gave you, it only had, it was using the name, the human-friendly name that we used in our state transition diagram. Okay, so let's go to a little design problem here and use all this stuff. Okay, I'm going to use the doorbell problem that we talked about in the review session. And let's explain this a little bit. So what happens here in this system is there's a doorbell, and when you push the doorbell, there's a little sequential circuit in it, and that doorbell sees the button go from unpushed to pushed, and when it does, it sends a 1 clock cycle wide pulse to some other circuitry someplace that plays music. Okay, so the doorbell circuitry just sends out a start signal when the button's pushed. That start signal goes to a whole nother block of circuitry. The doorbell has no idea what this other block of circuitry is doing. It just sends it a start signal, and this other circuitry just happens to be a music playing piece of circuitry. And that makes it very modular, and if you decide that you don't want the music playing circuitry anymore, you can replace that with a buzzer or flashing lights or whatever you want to do. The doorbell side of that circuitry doesn't really care. All it does is send out a start signal. So it's very easy to replace pieces of a system that's been built like that. Let's look at the doorbell. Doorbell has a state here where doorbell hasn't been pushed, and it sits there as long as the doorbell button has not been pushed. It sits there and sits there and sits there, and of course it doesn't want to send a start signal out, so its output is 0. It sits there, sits there, sits there. Now the button gets pushed, And now it goes to the start state. Okay, in the description of the circuit that I gave you, the start state, or the start signal that's sent out to the music player, it can only be high for 1 clock cycle. So since we're using a Moore machine here, you can only stay in the start state for 1 clock cycle, and then you have to get out of it. So remember, the output of a state in a Moore machine, so the output is connected with that state. As long as you stay in that state, you're going to have the output of that state. And if we only want the clock to be the start signal to be high for 1 clock cycle, you need to go in, stay for 1 clock cycle, and then get out. You can't stay in that state, or else you'll still be putting out a 1. So then you go to the next state, and I don't remember if I mentioned it, but if you have a so just a second, dog needs to go pee.